In this talk, I'd like to give a very quick overview of the area of community detection and present some of our contributions to the field. Community detection is a problem of finding communities in a social network. In more abstract terms, given a graph, we'd like to partition or cluster its nodes into densely connected subsets. This problem has many applications. For example, in spam and abuse area, if we have a graph where nodes represent users and two users are connected with an edge if they exhibit suspiciously similar behavior, finding a dense community may be an indication of some fraudulent activity. What are some desirable properties of an algorithm for community detection and its output? First of all, we'd like the clusters to correspond to ground truth communities. This means that we'd like them to be typically dense and sparsely connected with each other. In addition, we often look for a large number of small clusters. In the example from the spam and abuse domain, we don't expect many users to have suspiciously similar behavior to other users, and most clusters are going to be small. Also, if we want to partition users by their fine-grained interests, we don't expect clusters to be large. The algorithm for community detection is, ideally, it's very scalable so that it can handle large data sets. It has provable running time and quality guarantees. This allows us to predict its performance on unseen data sets. And then we also like it to automatically detect the number of clusters. This means that instead of taking the number of clusters that we'd like to get as a parameter, this is something that we typically don't know, we prefer to specify the desired cluster density. There are many different metrics and algorithms related to community detection, and in this short talk, I'm going to present only a few of them. One very popular metric for community detection is modularity. If we define by deg of x the degree of node x, by c of x the cluster of node x, and by m the number of edges in the graph, modularity of a clustering is defined using this formula. In this clustering formulation is very often used in practice, and the algorithm that's used to optimize for modularity is the Louvain method. This algorithm is based on a greedy approach. We start with each node in its own cluster, and then we improve the clustering using local moves. So a node tries to move to a neighboring cluster in order to improve the total objective. This algorithm gives very good results in practice, but unfortunately does not have many theoretical guarantees regarding the running time or the quality of the output. Another measure for the quality of a community or quality of a cluster is conductance. Let me give here a slightly simplified formulations for the sake of brevity. So the conductance of a cluster C, denoted by phi of C, is the number of edges leaving the cluster, marked in orange in the picture, divided by the total degree of nodes in the cluster C. So in this example, the total degree of nodes in the cluster is 10. The number of edges leaving the cluster is 2, so the conductance of the cluster is 1/5. A related measure is the normalized cut, and the normalized cut of a clustering is just the sum of cluster conductances. We recently identified one more interesting quality measure for a clustering that we called coconductance. So as you can guess, it's related to or closely related to conductance. It takes a single parameter, p greater than 0. The canonical setting is p equals 1. And the coconductance of a clustering is the sum over all clusters of 1 minus the conductance of a cluster raised to the power of p. If you want to find the clustering that optimizes for coconductance, when p tends to 0, the optimal solution is basically maximum matching. It contains the largest possible number of clusters that have at least one edge. On the other hand, when p tends to infinity, the optimal clustering is basically partition of the graph into connected components. The coconductance clustering problem consists in maximizing total coconductance of the clustering. And for p equals 1, this is very closely related to normalized cut. This is just the number of clusters minus the normalized cut of the clustering. So this definition is very similar to normalized cut, but we still think it's interesting because it has some interesting theoretical properties and it gives interesting results in empirical experiments. We give two algorithms for optimizing for coconductance. First is a practical algorithm based on the Louvain method, and this one has very good empirical quality. I'm going to present some results in the following slides. And the second is a theoretical algorithm, which works for p equals 1, and this one returns a constant factor approximation of the optimal solution, one that maximizes the coconductance. This algorithm runs probably in linear time. So let's move on to the empirical results. We used some data sets from SNAP in order to evaluate our algorithm, and here are the results on two of the data sets. In the red plot, we can see that coconductance slightly improves both precision and recall compared to the baseline algorithms. And in the left plot, we see that it improves precision in the high recall regime. Whenever we want to maximize precision at the cost of recall, other methods deliver slightly better results. Also, if we care about synthetic metrics, so for example, we want to optimize for cluster density, coconductance delivers good results, especially if we want to find a big number of small clusters. So to sum up, community detection is an active area of research. There are many algorithms and metrics for community detection, and there is no single solution that would work best in all cases. Now we added one more idea, one more algorithm and one more metric, which is coconductance, and we show that it delivers good empirical performance and has some nice and interesting theoretical properties. Thank you.